Hi everyone, my name is Shubhranshu. Today I'm going to talk about our work on entity resolution in dynamic heterogeneous networks. We are surrounded by time evolving dynamic networks. Here are some examples of dynamic graphs. On the left, we have a transactions network that underlies many of the banking e-commerce companies. Similarly, with the rise of ride-hailing apps, on the right we have a large transportation networks. A user product network that is implicitly formed in an e-commerce company, and a traditional email, phone or messaging network is shown on the bottom row. The common theme across all these networks is that they are dynamic in nature, that evolve in time. Our work addresses a representation learning problem in such a dynamic time evolving network. In particular, given a heterogeneous attributed dynamic graph with edge timestamps and node attributes, we want to learn a node representation that incorporates the attributes associated with the nodes, temporal evolution of the graph, and the graph structure. Before moving on, we broadly introduce the representation learning problem so as to familiarize ourselves with the on a high level with the representation learning framework. Representation learning concerns itself with learning a vector representation for a given graph element. For example, it could be nodes, edges, or even triangles. The underlying intuition is that we want to map these graph elements, such as nodes, to a d-dimensional vector space while preserving some notion of similarity. For example, we may want to capture similarity in terms of neighborhood. In that case, neighboring nodes in the graph should have similar vector representation. In vector space, similar vectors would mean vectors which are nearby in Euclidean space. Right? So as you can see here in the picture, like given a graph with any type of given embedding algorithm, we would want to project a target node with respect to its embedding. In particular, we talk about graph convolution networks that are one of the state-of-the-art graph embedding methods. We introduce GCNs here because we build upon the ideas of the GCNs. Consider the sample graph with only 5 nodes, here A through E, actually 6 nodes, A through F. Suppose we want to learn a representation for node A. Then what we do is we construct a computation graph with respect to node A as shown here. The computation graph expands based on the graph structure. Notice that nodes B, C and D are neighbors to node A in the input graph that we have on the left. Therefore, these nodes form the first layer in the computation graph looking from left to right. The computation graph can be constructed recursively based on the input graph that we have. Essentially, the computation graph lays out the structure of the neural network, where each of the gray boxes aggregate messages from the neighbors and apply a neural network. Here, suppose we want to capture the structure from neighbors of the neighbor. Thus, we have 2 layers in our network. In layer 0, embedding would be the input features of the node that we have. Now, let's take a look at the aggregation function in the GCN. The kth layer embedding in a GCN is given as sum of degree normalized embeddings of the neighbors from the previous layer. Degree normalization here accounts for the importance of a neighbor. Given the high level understanding of GCN, I will now introduce our approach to embedding learning. We call our embedding learning framework as TimeSage. The goal of TimeSage is to learn a temporal network representation. In order to capture how the graph has evolved in time, we leverage something called as temporal random walks. To understand a temporal walk, let's consider a sample graph, again a sample graph with 6 nodes where edges are time stamped. Given this graph, we walk from node, if we walk from node C to A to B, we would notice that this would be temporally invalid because we are going back in time. A valid temporal walk captures how the network evolves locally in time via ordered timestamps, which is why if you look at the path D, A and C, this forms a valid temporal walk. Right? In a dynamic graph, two nodes can have multiple edges between them and each edge has timestamp when two nodes have interacted. Right? So it could so happen that like for example, it could happen like for example, if you look at the edge C and E, this has two timestamps associated with that, which means that these two nodes interacted at two different timestamps. Now what we want to do is in time sage is that we want to learn the embedding by using convolutions through these temporal random walks. The idea is that these convolutions capture the important temporal dependencies within the network because the convolution is done over the temporal walk, and the weighted aggregation based on the visit count from the temporal random walk gives us the aggregation function over the network. Pictorially, if you look at, remember that in GCNs what we do is we aggregate the messages from the neighbors. Here what we do is we have a weighted neighbors based on the temporal random walk that we start from the target node. Now given now that we have defined our network, we train our network in an unsupervised setting through hinge loss function. The intuition for using hinge loss is that the dot product between the neighbors should be greater than that of a non-neighbor by at least delta, which is a tunable hyperparameter in our case. In addition to time sage, we also introduce a simple version of time sage that incorporates temporal information via weighted edges. The underlying idea is that a recent edge is weighted more compared to an edge which is older in time. We then apply GCN over the graph with weighted edges. In order to look at the details of the aggregation function, you can check out section 3 of the paper. We carry out experiments and compare our proposed method with the following baselines. Where if you look at our method time sage has all the desired properties in an embedding framework. CTDNE is a embedding framework which is embedding technique which captures a temporal dependency by using a word-to-vec kind of embedding mechanism, again on the temporal random walks. And node to bits is another embedding approach which extends the capability of CTDNE that can incorporate the node attributes. This is currently, to the best of my knowledge, is the state of the art temporal embedding method that we have. Here are the following public datasets that I used and which are publicly available at networkrepository.org with varying number of nodes and number of edges. The first task that we set up is a link prediction task where in phase 1 we use 75% of the edges for learning the embedding, and in phase 2 what we do is we use 25% of the held out links as positive examples, and then we sample equal number of negative edges from the graph. Here edge representation is arrived at by using the Hadamard distance between the two nodes. Here we compare the results of all the methods against our proposed method time sage and a simple variant, simple time sage. across various dimensions. So we look at dimensions from 128 through dimensions 10 um, and dimensions 64 and 32. So there are four values of dimension that we check out. And if you notice, time sage kind of outperforms in majority of the dimensions for these two data sets, while simple time sage remains competitive. We observe the similar results where on the other two data sets. However, what we notice is uh, time sage performs really well even when the number of dimensions is really small, like for example only 10 dimensions. And in both the results, on the y-axis what we have is area under the curve of ROC metric. Since the classes are balanced, we use this metric to compare the results for across methods. However, motivated by these results, we apply our method to a real world use case where the problem is of a company X e-commerce fraud detection, where in this company what happens is that a large percentage of all transactions are declined by bank, or they are flagged by the company's fraud detection system itself. It turns out via analysis that large part of these fraudulent transactions are instances of something called as credit card testing fraud, which is nothing but a case where fraudsters carry out small transactions to find out which stolen cards are working. And because of these fraudulent transactions, it results in multiple losses for the company. So our goal of the problem was to identify and flag transactions for possible card testing fraud. Here what we do is we represent the transactions in the graph as nodes into a dynamic multigraph, where edges encode the transaction timestamp and pairs of nodes can have multiple edges. Remember, this is a heterogeneous network which has four types of nodes in this case, which is email, IP address, device ID and credit card identifier. And the goal is to link entities that could potentially be fraudster. We used checkout transactions and represented this as heterogeneous graph with like about 1.5 million nodes and 2.5 million edges with 4 entity types, and each of the nodes had 12 attributes associated with those. We carried out two different tasks. One is link prediction as introduced for the public datasets, and a fraud detection, which is a node classification problem, where what we did is we created a node classification dataset via a human annotated set of fraudulent nodes, approximately 5,000 nodes, and then we use the node embeddings as features into a binary classification problem. So if you look at the results for both tasks, whether link prediction and fraud detection, it turns out that our time sage based methods are methods that incorporate temporal information through convolutions through convolution or through weighted edges, temporal weighted edges, outperforms the competition. Notice that we did not include CTDNE because CTDNE cannot handle attributed networks, so we have not included the results for the CTDNE in our comparison. One important thing here is that for the link prediction task, if you look at even simple time sage outperforms the proposed time sage. The reason, which highlights the fact that for link prediction task, the recency of a transaction is more important for predicting the next link. With these results, time sage has shown promising results, and it could be used in many practical cases. For example, in this case, for company X fraud detection problem. Thank you, everyone. Thank you for your time. I would like to apologize for not presenting live. Currently, it is 3 a.m. in my time zone. However, I would request you to write to me with any questions that you may have at the following email ID. Thank you for your time.